Hey everyone, welcome back to another prep video, and in this video we're going to talk about question number 2 from the 2020 US Open Contest Bronze, Social Distancing 2, or also known as SocDist2. So let's just read it. Farmer John is worried for the health of his cows after an outbreak of a highly contagious bovine disease, COVID-19. Notice the pun, COVID-19. So despite his best attempts at making N cows practice social distancing, many of them still unfortunately contracted the disease. And the cows are conveniently numbered 1 through n, and are each standing on distinct points along a long one-dimensional number line with cow I standing in position x of I. Farmer John knows that there is a radius r such that any cow standing up to and including r units away from an infected cow will also become infected and then pass the infection on along to additional cows within r who are r units away, and so on. Unfortunately, Farmer John doesn't exactly know R, but he does know which of his cows are infected, and given this data, we're asked to find the minimum possible numbers of cows that were initially infected with the disease. So first, for the input format, first we're given n, and then each of the next n lines describes one cow in terms of two integers x and s, where x is the position and s is like whether it's sick or not. So it's 0 for a healthy cow and 1 for a sick cow. And at least one cow is sick, and all cows who could have possibly become sick have already become sick. And we're asked to output the minimum numbers of cows that could have been initially sick prior to the spread of any disease. So let's just take this data and then try plotting it out and see what happens. So the first thing we want to do is I always recommend that we put this in order. So we see 1, 3, 6, 7, 10, 15. So if we put this in order and make a number line, it's really not exactly straight, but like 1, 3, 6, 7, 10, and 15. And then we also should check which ones are infected, and it seems like the only cow that's not infected is number 10, so I'll just put a 1 on all the ones that are infected. So we notice how they mention that there is a radius r in which any cow standing up to and including those r units will become infected. And we just need, in order to find the radius, I would say that we need to find the minimum distance between a healthy cow and a non-healthy cow. So in this case, we have a cow at 0, and we have a cow at 10, and it's not infected, but the cows surrounding to it are infected. So the distance from here to here is 3, while the distance from here, 10 to 15, is 5, meaning that our distance is actually 3. So what we can do now is, what I'm going to do first is actually try finding r, and then we can calculate how many initial cows are infected after that. So I have set up my input files with copied and pasted data and my output file, and now I'm just going to start it. So obviously we're going to need fstream, just to file read, and then we're going to need algorithm. And in order to use algorithm, what we're going to do that for is for sorting, because we notice that initially our data comes without sorting, but we actually want to sort it so that it's easier to figure out. So we're going to do that, and then we're going to use namespace standard, obviously, and then read in our data from SocDist2 and output it to SocDist2.out. Okay, and now what we can do is we notice that we have int n, and then I'll also use vectors because vectors are cool. So we'll also use vector, and then we can create our main function. So here we go. And then what I'm also gonna do is actually create a structure. So kind of like a class in Java. So it's gonna be struct cow. And I think this will help us with sorting it, and sorting it based on the position and not based on sickness, right? So we can do that. So struct cow, and we get a position and whether it's sick or not. So I'll just keep that as an integer, and that's our struct. And then I'm also going to create a vector of these cows. Cow, and I'll call it vec, because yeah, generic names. So then I'll input n. What we'll do after that is we will create a for loop int I is equal to 0, I is less than n, I plus plus. And then what we're going to do in that is create two integers I'll just call them x and s, just kind of dummy data for the two integers that we will expect, x and s, and then I'm going to pull them in, and then I'm going to pass them in to our vector. So using pushback. So then I'll create I'll pass it in, and then we have our basic input. Alright, so now we have to sort it. We have to sort it right now, because otherwise right now it's in unsorted order, and then finding r would be kind of hard. So I'm going to do begin vect, and then the end of vector, and then I'm going to sort it using a quick lambda function. So const cow and x and cow and y, and then it's going to return x dot position pos is less than y dot position, and then obviously a semicolon and then another semicolon, and there we have our sort function, right? And now what I'm going to do is solve for the minimum r. So I'm going to create a variable min r, and I'm going to set that to 1, basically a billion, and then every single time we're going to keep on going lower as we find smaller and smaller r's. So that's basically what I'm going to do. And what I'm going to do after that is create a for loop, and in that, what I'm going to do in order to find the smallest r, what I'm going to do is check that if some position is not sick, I'm going to check the positions to the left of it and to the right of it, right? So in order to do that, I'm going to say if our vector at I dot sick is equal to 0, meaning that it's not sick, I'm going to create a variable r. So int r is equal to 189, and this is kind of our temporary r that we're going to try and simulate and see if and we're going to assign a value to this, and then check at the end which one is smaller between the previous r and the current temporary r that we have. So I'm going to say that if vector at I plus 1 dot sick is equal to 1, meaning that it is actually dot sick is equal to 1, meaning that it is actually sick, then I'm going to say that our r is equal to the vector at I plus 1 dot position, so basically the next value's position, minus vector at I dot position, and then minus 1. Alright, so that would be our formula for basically finding it, because for example over here 10 and 7, and 10 minus 7 is actually 3, but it's not, we want it to be like the number that's less than that, so it should be technically be 2, because if it was 3, then the disease would have spread from 7 to 10. So basically we just want to find the one number below that, so in this case it would be 2. So that's why the minus 1 exists, and we're also going to check the other side, basically the one that's below it, so vector at I minus 1, if that is sick, if that is sick, then what we're going to do is basically the same thing. So I'll just copy and paste this here. And instead of I plus 1, it's going to be I minus 1. And then, after that, we're just going to say min r is equal to min r. So basically the previous r and and r. And also, since we're doing a few things over here, for example, we're checking like I minus 1, we can't exactly have an I is equal to negative 1, so I'm going to start off with I is equal to 1. That's basically what I'm going to do. And then that should be all we need for finding r, so let's just try printing out r. Min r, and see if that works. So in this case, our min r should be 2, and it does work, it does seem to work, so I think we can call that good. So now what we want to do is solve for how many cows are initially infected. So in order to do that, I'm going to kind of clear all of this R data over here. So in order to do that, let's just try figuring out by ourselves, given our R, what it is, before we try to think of a way that our computer could solve it. So our R in this case is going to be 2. So let's say 1 was an initial. Let me just remove all of these. Actually, let me keep them. But then what I'm going to do is just add kind of a circle to indicate that it was an initial cow. So let's say 1 was the initial cow, right? then it would have spread to 3. So there's no need for 3 to already have contracted the disease before. But if we want to look between 3 and 6, we figure out that the jump is too large for like the r is in the distance between is 3, but 3 is bigger than our r of 2, meaning that 3 couldn't have spread its disease to 6, meaning that this would have also had to been an initial cow, and the distance between 6 and 7, which is 1, is less than our r, meaning that it could have spread. And between 7 to 10, that doesn't matter because it is not infected, so we know that the 10 doesn't really matter. And we know that the distance between the 15 and the 10, because 10 is 0, there's no way it could have spread the disease to 15, meaning that 15 would have also had to been an initial cow. So how are we going to find out how many initial cows are there? And in order to do that, we're kind of going to do the exact same process that we did first. So we're going to start the first cow and check, we're going to start the first cow and check, is it infected? And if it is infected, then we know that's the initial cow. We're just going to set it as the initial cow. And we're going to move to the next cow, and we're going to check how much is the distance from the previous cow. If the distance from the previous cow is less than or equal to r, then we know that it would have been able to spread, and that means there's no need for 3 to be an initial cow. And there's also another possibility that the previous cow, for example, let's imagine that 1 was actually not an infected cow, then we would have also known that 3 would have to be an initial cow because it can't really spread from a non-infected cow to an infected cow. And then we're going to move on again. So we check over here, what is 6 minus 3? Since both of the cows are infected, we can check that. And we figure out that it's 3, which means it's greater than our r of 2, which also means that our 6 had to be an initial cow. And we move on to the next one. Since both of these are infected, they could have spread diseases from one each other. So 7 minus 6, the distance is 1, which is less than our r, meaning it could have spread. And then we go to 10, and we check, well, it is actually, we check that it's not infected, so it can't be an initial cow. Then we move to 15, and there we check that, basically we check that the previous cow actually was not infected, meaning that this also had to be an initial cow over here. So that's kind of like the algorithm that we're going to use. So what we're going to do is a for loop in I is equal to 0, I is less than n, I plus plus. So we're automatically going to assume that if our first cow is infected, then that was an initial cow. So I'm going to say if our I is equal to 0, I, and then our vector at I, and if its sickness was categorized as 1, meaning it was infected, then our initial cows is going to be incremented. And obviously I forgot to initialize the initial cows. So initial cows is equal to 0. Except I spelled it wrong. Yep, initial cows, there we go. And obviously we need to give it a type, so int initial cows is equal to 0. Alright? So now that we have our initial cow out of the way, now what we're going to do is apply it to the rest of the cows. So I'm going to say else if the cow at that vector I is actually sick, then we're actually going to commence a check. So if the previous cow is not sick, then we obviously know that it has to be an initial cow. So that would be an initial cow plus plus. Otherwise, we can also check that if the distance between the current cow and the previous cow was greater than the minimum r that we set, like the radius that we set, then that would also have to be a initial cow. So we can say that vect at I minus I dot position minus vect at I minus 1 dot position, if that is greater than the minimum r, then we're also going to increment initial cows. And then that's basically it. Then we can return what our initial cows is. And let's just try running this. And we see that it's 3, which matches up with what we originally were supposed to get from this sample input. So now I'm going to try submitting this and see what happens. Yep, so I'm about to submit my file over here. I notice I'm using C++11 because what we use over here, the lambda function, is actually, I don't think it's supported by previous versions, so we have to use C++11. And let's just submit this and see what happens. And we see that it works out, so that's good. So that means our solution for this was good. And yeah, this was a fairly interesting problem. We had to do a few things with it, and it worked out fine.